Hey everyone, welcome back to my channel. In this video, I'm going to be going over ordinary differential equations and giving a definition of what they are. But before diving into ordinary differential equations, I think it's important to go over this general concept of a differential equation. So there are a lot of definitions for this floating around, but one that I saw that I like the most is a differential equation is an equation that expresses the relationship between a function and one or more of its derivatives. So once again, a differential equation is an equation that expresses the relationship between a function and one or more of its derivatives, and I'll give some examples of these here shortly. When we study differential equations, we're usually studying one of two categories of differential equations, and most of the time we're either looking at ordinary differential equations, which are ODEs, or partial differential equations, which are PDEs. And even though this is going to be a video on ordinary differential equations, I still think it's really useful just to start off with an example of a partial differential equation, because seeing that, I think, will give a better understanding of what an ordinary differential equation is. So let's say that we have the following function, and I'm going to call this function z of x, y, and I'm just going to say that it's equal to x plus y squared. Now, one thing I notice here, I have two independent variables, and that means that I can take partial derivatives. So let's say that I take the partial derivative of z with respect to x. So I'll call this del z del x. This is assuming that you've had some calculus knowledge and that you're familiar with ordinary derivatives and partial derivatives. But just a quick summary. In order to take the partial derivative of this, I'm going to basically treat my outer function as some u squared, which the ordinary derivative of that is going to be 2u. And then I'm going to take the derivative of the inner function with respect to x, which the derivative of x plus y with respect to x is just 1, because the derivative of y with respect to x is 0, the derivative of x with respect to x is 1. So when we take the partial of z with respect to x, that's going to just be 2x plus y. And I can do the same thing. I can take the partial of z, the partial of z with respect to x. I can do the same thing. I can take the partial of z with respect to y, del z del y, and that's going to give me the exact same thing, because once again, for my inner function, I'm just taking the ordinary derivative of y with respect to y, which is 1, the ordinary derivative of x with respect to y, which is 0. So this is just going to give me 2x plus y again. And I can actually say from this that the partial of z with respect to x is equal to the partial of z with respect to y. And this right here is an example of a partial differential equation, so a PDE. And what makes this unique is this satisfies the definition of a differential equation that we just began with. It's an equation that expresses the relationship between some function and one or more of its derivatives. But this is a partial differential because our function has multiple independent variables and we're working with partial derivatives. Okay, so next, let's go into ordinary differential equations. Okay, now let's dive into ordinary differential equations, and I think we can begin again with a function as an example. So let's say that I have the following function. I have f of x equals log of x. And I want to start taking some derivatives of this. Notice I only have one independent variable. I just have x, so I can take ordinary derivatives from calculus. F prime of x, or the derivative of log of x, is going to be 1 over x. Now, I can keep taking more and more derivatives. Let's say that I want to take f double prime of x, or the second order derivative. That's going to give me negative 1 over x squared. And just as a quick aside, I'm really just taking the derivative d dx of x to the negative 1. So we're putting the negative 1 in the coefficient and then lowering the value of that exponent by 1. So this really becomes negative x to the -2, which is why we have 1 over x squared. And then I'll just take one more derivative. I'll take f triple prime of x, and I'll keep going. That's going to give me 2 over x cubed. Now, all of these are examples of ODEs, ordinary differential equations. What makes these unique from the partial differential equations is that we're dealing with a function that just has a single independent variable, and we're taking ordinary derivatives, which is what makes this an ordinary differential equation. And it's all right to use different notations for the derivative. Here I'm using f prime. You can always use y prime if y equals f of x. You can also say df dx. These are all acceptable notations that you see with ordinary differential equations. That's the general definition of it. Let's write something more formal out, okay? All right, and now we have a more formal definition of an ordinary differential equation. So let f of x be a function defined on an interval I. An ordinary differential equation is an equation involving x, which is our independent variable, the function f of x, and one or more of its derivatives, which is what we've been going over this whole time. This is just for the sake of the definition. The function can be f of x, y of x, and whatever, and obviously we don't have to call our independent variable x, but this is just as an example. Okay, let's go over a few more examples of some ordinary differential equations. Okay, now let's look at some examples for ordinary differential equation. The first one we could look at is dy dx equals sine of x. This satisfies our original definition for a differential equation. It's an equation that expresses the relationship between some function, in this case that function is y, and its derivatives. And then for this example, we see that we only have an ordinary derivative with respect to x. So a single independent variable, which makes it an ordinary differential equation. Next, let's look at, we can do dy dx minus y equals x. In this case, the function that we're showing a relationship with is the function y, and we have a single independent variable x. We're using ordinary differential or ordinary derivatives, but it's important to notice this y might look like a variable at first. Maybe I have x and y. But because I have this notation, dy dx, I know that y is actually a function. So I have y is a function, and there's only one variable here, which is x, ordinary derivatives. So ordinary differential equation. And one more example, let's try f prime of x equals f triple prime of x. In this case, our function is f of x. We're looking at derivatives of higher order here, where we have a single derivative and a third order derivative, but it still satisfies that definition. It's a relationship between some function, and it's an equation that shows the relationship between a function and one or more of its derivatives. And here the only independent variable that we have is x, so single independent variable and ordinary derivative. So these are all ordinary differential equations. One thing that's important to note, when we're usually solving equations, we're usually trying to solve for the variable. But when we're solving for differential equations, the thing that we're looking for is the function. So it's the function that we're trying to solve for, which is why in these examples, I don't actually show the function. The point of getting into differential equations is it gives you the tools that you can use to figure out what this function should be. So that was just an introduction into ordinary differential equations. In a later video, I'd like to actually go into the common properties of ordinary differential equations, or the important properties of ordinary differential equations, and later on we can go into some of the methods for actually finding solutions. Also, I just want to note, when I do research to make these videos, I look through various resources, but for this video, the one resource that I use the most is this book, and this is Ordinary Differential Equations by Morris Tenenbaum and Harry Pollard. This is an excellent book, but I at least wanted to shout this out. This is very well written, easy to follow along with. So this was kind of my main reference for these topics, just so that I'm not ripping anyone off. But I hope this video was useful. Please let me know if you have any comments, suggestions for how I could make this better, or just anything really in the comments. I really appreciate it, and I hope you have a great day. Thank you.